Welcome to a course on sequence and series. In this lecture, we are going to see some properties of a Cauchy sequence and some theorems related to it. Right? Without any delay, let us get into the lecture. You may see the statement of the theorem that we are going to see in the screen. First, we are going to prove in any metric space, every convergent sequence is a Cauchy sequence. Okay? Okay, let us get into the proof. What is given? It is given that in any metric space we are talking, right? So in any metric space we need to take some convergent sequence. Let Pn be a convergent sequence in X. Okay. By the definition of a convergent sequence, what can we say? By definition, for every epsilon greater than 0, there exists what let me say n, there exists a positive integer n such that d of Pn comma p less than epsilon or epsilon by 2. I am taking this to be epsilon by 2. Okay, for n bigger than or equals n. Okay, whenever this is true, I may also write d of Pm comma p less than epsilon by 2 for m bigger than or equals n. It is just a matter of notation, right? So after this stage I may take any point. Okay, after the stage n I may take any point, and the distance between the point and the limit is negligible quantity, right? So it's a convergent sequence in X which converges to P. Okay, this is the assumption that we have made. Now consider d of Pn comma Pm. What is it? Using the triangle inequality, we may write Pn comma P plus d of P comma Pm, and this is epsilon by 2 and this is epsilon by 2, hence it is epsilon. This is true only if n bigger than or equals n and m bigger than or equals n, which means what we have is d of Pn comma Pm is less than epsilon for n comma m bigger than or equals n. So after a stage I may choose any 2 points in the sequence. The distance between those 2 points is a negligible quantity, right? So that in order to get epsilon here, we have chosen epsilon upon 2 here, right? Remember, I was keep telling this, epsilon is a negligible quantity, so you may choose your epsilon to be in the way you want, right? Now in the second part of this theorem, what we are going to prove, if X is a compact metric space. Okay, in a compact metric space we have a Cauchy sequence, right? In a compact metric space we have a Cauchy sequence. In that case we'll have to prove that Cauchy sequence is convergent. Okay, let us see how it is proved. Okay, here in the second part of the proof, what are we doing? We have a compact metric space, right? So let X be a compact metric space, okay, in which we are taking a Cauchy sequence, be a Cauchy sequence in X, right? Now we need to prove the sequence is convergent. This is what we need to prove in this part. Okay, here let me choose En as the points Pn plus 1. We are choosing the collection of points, okay, for n from 1 to, and it goes this way. Okay, we are collecting the points in the sequence in the form of En. Okay, this is a set, right? What is the sequence? The sequence is a Cauchy sequence. We have rephrased the definition of a Cauchy sequence with the help of a diameter concept. So then what we have, limit n goes to infinity, diameter En is 0. Okay, we also know that diameter En is same as that of diameter En closure. Hence, limit n goes to infinity, diameter En closure is 0. Okay, let us mark this one because we are going to use it in the upcoming part. This is what we have. Now, what kind of set this is? Okay, closed set, right? This is a closed set. Where? In X. So, En closure is a closed set in a compact metric space X. We can come to a conclusion that En is compact. Okay, using the result that closed subset of a compact set is compact. Now you just treat this as a compact set. Forget about the metric space and all those stuff. This is a compact set. In this compact set, it is a closed subset, right? Therefore, it is compact. Okay, and here what is happening? From this idea, you may see E1 is P1, P2, P3, etc. and it goes on. E2 is P2, P3, this goes on. So, your En contains En plus 1. Okay, so this implies what? This implies En closure contains En plus 1 closure. So we have proved any En closure is compact and you have a sequence of compact sets. Okay, therefore what you are getting? Therefore intersection En closure, okay, where n runs from 1 to infinity consists of exactly 1 point. This is what we have proved in the previous lecture. Let us say that point as P. Okay, now we are going to make use of this one. Okay, as n approaches infinity, your diameter is going to be 0 and this intersection is going to consist of only one point P, which means this P is present in all the sets En closure. Right? Now, here, come back to here. As n approaches infinity, this is 0. So, when your n is becoming large and large, it is going to consist of only one point and that point is P. So, after a certain stage, the distance, that is the diameter, has to be some negligible quantity, right? So that when your n approaches infinity, it can become 0. Right? Thus, for every epsilon greater than 0, there exists some stage. Okay, there exists a positive integer n naught. Since we have used the n notation here, these are just notations, okay, such that diameter of En closure is less than epsilon for n bigger than or equals n naught. Okay, what is this? So this is distance of P comma Q less than epsilon for every Q in En bar and n bigger than or equals n naught. Okay, after this stage, for every element in the set, this is going to be the case because P is the point which is present in all En closure, right? So what kind of points are present in En closure? We know that En closure is the union of En with the limit points of En. I don't know what are the limit points of En, so forget about it. But the points of En are present in En closure, right? So the points of En are of this form. Hence, this implies what? Okay, let me use the space. Okay, that implies T of P comma Pn is less than epsilon for n bigger than or equals n naught. Okay, after this stage, this is going to be the case. Okay, after this stage, all the points in n I am talking. Okay, all the points in En closure I am talking. En closure is going to consist of these points along with its limit point. I forget about the limit point. Okay, as of now I forget about the limit point. All the points in this En is going to satisfy this condition. That is important to me. Okay, this tells me what? After a certain stage, the distance between the points in the sequence and the point P is a negligible quantity, hence Pn converges to P. Right? So in the third part of this theorem, what we are going to prove is in Euclidean metric space. Okay, whenever we talk about a Euclidean metric space, we are considering the set Rk with standard Euclidean metric. Okay, in Euclidean metric space, every Cauchy sequence is a convergent sequence. That is what we are going to prove in the third part of this theorem. Okay, in the second part of this theorem, we have proved something different. That is, in compact metric space, every Cauchy sequence converges. Okay, in the third part of the theorem, we are going to prove in Euclidean space, every Cauchy sequence is convergent. So, can we say Euclidean spaces are compact metric spaces? No, we cannot come to that generalization, because at the end of this theorem or in the upcoming lecture, we may see some counter example that Euclidean spaces are not compact metric spaces, whereas in the theorem what we are going to prove is that in compact metric spaces Cauchy sequences are convergent, and in Euclidean space also Cauchy sequences are convergent. Right? So in the third part, let me consider, let Xn be a Cauchy sequence in Rk. Right? So if we talk about Rk, that is the Euclidean space, the metric defined here is standard Euclidean metric. Okay, that we have to always remember. Next, I am defining En to be the points xn plus 1. Just we have defined in the previous thing. Okay, for n this way. Right? So now choose some n such that diameter of En is less than 1. This is possible. Okay, because Cauchy sequence in the sense after a certain stage, what is going to be thing? So this implies what? Absolute of x minus y xn comma xm is less than epsilon for n comma m greater than or equals n. So after a certain stage, the distance between these 2 points is going to be some negligible quantity. I am choosing this negligible quantity to be 1. Okay. So whatever may be the value of epsilon that we choose, we can always find a positive integer n such that this is happening. So such type of n I am choosing such that the diameter is what? Supremum of the distance. Okay. That is going to be less than 1. Here, the range, let me name the range as E of xn is a union of En. Okay, this En. Here I have chosen some n, right? This En and the finite set. What is the finite set? This is going to collect the points from xn. So the finite set is going to collect the points of this form. Okay, make a union of this one with this En, you will get your entire range. Okay, so this is a finite set and the diameter is less than 1. The diameter, again, let us recall the definition of a diameter. It is the supremum of the distances between the points in En. So this tells you your En, the set En is a bounded set, right? When your En is not bounded, you will have your diameter to be infinity. Since En is bounded, you are getting something of this form. And this is a finite set. When you make finite sets are always bounded, right? So you are making a finite union of a finite set with the bounded set. Hence, the range E is bounded. Right? I have a bounded set. And we also know that, what is this? This is closed. Whenever E is bounded, E closure is also bounded. Okay. Instead of, we know that this implies these things are happening. Okay, in where? In Rk, right? So what is Rk? It is a Euclidean metric space. Right? In a Euclidean metric space, you have a closed and bounded set. This implies what? E closure is compact, right? Now, you may treat the sequence Xn as a sequence in E closure. Right? You have a Cauchy sequence in what? In a compact set. Now you may treat this as the metric space, okay, submetric space of Rk. Now you may treat this as the metric space, which is a compact set, therefore it is a compact metric space. You have a Cauchy sequence in a compact metric space by the second part of the theorem that we are discussing now. Okay, you may say Xn converges to some X in E closure. Okay, in the previous result also we have proved the convergence in that compact metric space. Okay, so it converges to some point of that metric space. Here it converges to some point in the E closure, which is a subset of Rk, right? Hence Xn converges to X in Rk. Here this X is taken in E closure, right? This converges in Rk. Therefore what? Every Cauchy sequence converges in Rk. So the second part of this theorem and this part of this theorem tells you you don't need to know about the limit of a sequence to say whether the sequence is convergent or not. If you are talking in a compact metric space or in a Euclidean space, right? These are two different kinds of spaces, right? In a compact metric space or in a Euclidean space, if you can identify some Cauchy sequence, that is going to be convergent. Without even identifying the limit of a sequence, we can talk about the convergence of a sequence. That is the idea which we can get from this theorem, right? And in the third part, every Cauchy sequence is convergent in Euclidean metric space. This is known as the Cauchy criterion for convergence in Euclidean spaces, right? In order to identify whether a sequence is convergent or not, it is enough to identify. It is enough to check that sequence is Cauchy or not. It is enough. Now let us make some remarks based on the theorem that we have just seen. That is, in Euclidean spaces and compact metric spaces, a sequence is Cauchy implies that is convergent, right? Okay, before making the remark, let me define something. A metric space, okay, that may be any metric space, is said to be complete. So this definition is all about the complete metric spaces. Okay, a metric space is said to be complete if every Cauchy sequence, okay, let me name that metric space as X. Okay, a metric space X is said to be complete if every Cauchy sequence converges in X. Okay, so if you take any Cauchy sequence in that metric space and can prove that is convergent in that metric space, you can say that metric space as a complete metric space. So in Euclidean spaces and in compact metric spaces, you have every Cauchy sequence are convergent. So these two are examples of what? Complete metric spaces. Okay, here C denotes the compactness, right? These are complete metric space. And if you take any closed subset of a, let me take E to be closed subset of compact metric space. This also becomes what? This also becomes a complete metric space with the same metric, that is defined on this compact metric space. Therefore, this is also an example of any closed subset of a compact metric space is also a complete metric space, right? So then E is also a complete metric space. Okay. Now, in Euclidean space itself, if we are talking about Euclidean space, the metric defined on this is absolute of x minus y, right? Can we guess some space with the same metric but it's not a complete metric space? Yes, of course we can identify set of rational numbers. Consider the set of rational numbers with the standard Euclidean metric. Okay, this is not a compact set, as well as this does not come under Euclidean space. Here you may identify some Cauchy sequence, but it's not convergent. If you want an example, I can give. Consider this sequence. Okay, you just consider this sequence, and easily you can prove this is a Cauchy sequence, but it is not convergent. Because in order to prove it is Cauchy, you will just have to take the absolute of two terms after a certain stage, whether the distance is negligible or not, that you can see. Okay, and this of course this is convergent when you treat this as the sequence in the set of real numbers, and it converges to the quantity E, right, which is an irrational number, which is not present in the set of rational numbers. Okay, so this is one of the example of a Cauchy sequence in the set of rational numbers, which is convergent in the set of real numbers, but not in the set of rational numbers. Hope you have had a quite better understanding of Cauchy sequences and the related results. In the upcoming lectures, we are going to work out some problems on the Cauchy sequences and few more results to work out the problems on sequences. Thank you for watching.